In this session, we're going to solve linear systems of equations by substitution and elimination. And at this point, we are talking about 3 by 3 systems, which means we have 3 variables and 3 equations. Our general strategy is that given a 3 by 3 system, we want to eliminate a variable using a pair of equations. Pick another pair of equations and eliminate the same variable. If we do that, we end up with a 2 by 2 system. We solve those as before and start back substituting in order to get the full solution to the system. We'll see how this works. First, an example of an equation in 3 variables. You might see something like 3x plus 5y minus 7z is equal to 10. Okay, so this is our linear equation in 3 variables, and what it represents is a plane in space. So when we were solving 2 by 2 systems, what we had were lines that intersected on a plane, and we wrote down the point of intersection as an ordered pair x comma y. Here, since we're talking about a plane, and we're talking about 3 of them, right? It's a 3 by 3 system. We're talking about points of intersection between 3 planes. There are several possibilities that could happen. When we have 3 planes, we could have a situation in which there are no points on all 3 planes, right? They don't coincide at any particular point. This would be a picture of no solution, right? You got 2 parallel planes, and then 1 plane cutting through the both of them. The 3 planes could intersect at a single point. And in this case, we would give the solution as an ordered triple x, y, z. We could also have the 3 planes intersect along a line, in which case we would, well, we'll see how to write that down in a different video. This, where they intersect along a line, would be called a dependent system. And if the planes share no points in common at all, that would be an inconsistent system. And the case in which they intersect at a single solitary point is the focus of this particular video. So once again, our general strategy. Take a system that has 3 equations and 3 variables. Eliminate the same variable twice to get a 2 by 2 system, which we know how to solve based on previous information. Let's begin. Give the complete solution to the system of equations, and our system is x minus y plus 2z equals 2, 3x plus y plus 5z equals 8, 2x minus y minus 2z is equal to negative 7. I've got a couple of competing thoughts here. One is I could eliminate the x's if I multiply by appropriate constants and add equations together. Seems to me that's a little bit of work I don't want to do. I could eliminate the z's from the first and third equation, but then I'd have to multiply to eliminate it from the second equation. I'd rather not do that. Looking at this kind of holistically, it looks like it would be relatively easy to eliminate the y's twice. That's what I'm going to do. I'm going to number the equations 1, 2, and 3 just to make it easier to talk about them. Seems like I could eliminate the y's by adding together equations 1 and 2. So I'm going to write that down below here. So rewriting equations 1 and 2, we have x minus y plus 2z equals 2, 3x plus y plus 5z equals 8. When I add these 2 equations, the y's get eliminated. We get 4x plus 7z is equal to 10. I'm going to call it equation number 4, and now I'm going to use equations 2 and 3 to again eliminate the y's. So as before, I'm going to rewrite equation 2 and equation 3. I don't have to multiply by any coefficients because the coefficients of y as they sit are 1 and negative 1. But if I had to multiply, I would, as with 2 by 2 systems and using elimination. Well, let me rewrite these equations here. And I'm adding together 3x plus y plus 5z equals 8, and 2x minus y minus 2z equals negative 7. again eliminating the y's. It is essential that we eliminated the same variable twice, because now when I add these together and get 5x plus 3z is equal to 1, I'm calling that equation 5, and when I put that up here by equation 4, 5x plus 3z is equal to 1, now I have a 2 by 2 system. You see it's got the same two variables. That I'm going to rewrite down below here. Okay, so I've got 4x plus 7z equals 10, 5x plus 3z equals 1, and now I want to pretend that this is a brand new problem. I want to solve this system by elimination, I'm going to say. And to do so, I'm going to multiply both sides of the first equation by 5, and then both sides of the second equation by -4. And when I do that, what I'll be doing is I will be eliminating the x's, although the choice of variable up to here is really up to you. So multiplying equation 4 by the number 5, I get 20x plus 35z equals 50. Multiplying equation 5 by the number -4, I get negative 20x minus 12z equals -4. When I add those two equations together, the x's get eliminated, and we end up with 23z is equal to 46, which means that z is equal to 2. I can take that z and put it into either of the equations that have x and z in them. I'll use 5x plus 3z is equal to 1, and so I have 5x plus 3 times 2 is equal to 1. So 5x is equal to -5, and x is equal to -1. Now I have z, and I have x. What we now need is y. For that, I look back at the original system. We can use any equation from the original system. I'm going to use equation 1. So we're going to take z is equal to 2, and x is equal to -1. We're going to put those into equation number 1. So that gives me -1 minus y plus 2 times 2 is equal to 2. Simplifying gives me that -y plus 3 is equal to 2, which then means that y is equal to 1. So now I know what x is, I know what y is, I know what z is. I'm not going to give you a scavenger hunt. I don't want you to give me a scavenger hunt. Write your answer in an ordered triple. X, y, z, the ordered triple, is equal to -1, 1, 2. Next we have a system that people think is hard, but actually turns out to be easier. It's 2y plus z equals 3, 5x plus 4y plus 3z equals -1, x minus 3y equals -2. What makes it seem hard is that we have missing pieces. What makes it actually easier is that we have missing pieces. Remember that our general strategy is to take a 3 by 3 system, eliminate a variable, and end up with a 2 by 2 system, right? Now that 2 by 2 is 2 equations with 2 variables. I already have an equation with 2 variables. In fact, I have 2 to choose from in this case. So numbering our equations 1, 2, and 3, well, we just have to decide what variable we want to get rid of. I'll give you a big old hint. Since y is in all 3 equations, don't get rid of y. How about if we use equations 1 and 2, get rid of z, and then use that resulting equation together with equation 3. So equation 3, I'm just going to rewrite it over here. X minus 3y is equal to -2. And then to make eliminating z work, what we're going to do is we're going to take -3 times equation 1 and add to it equation 2. So -3 times equation 1 is -6y minus 3z equals -9. And then just rewriting equation 2, 5x plus 4y plus 3z equals -1. And then adding these two together, we'll eliminate the z terms as promised. We have 5x minus 2y is equal to negative 10. That I'm going to call equation 4, and I'm going to put up above equation 3 here. And now we have kind of like a brand new starting point. This system, 5x minus 2y equals negative 10, and x minus 3y equals negative 2. Equation 4 I'm going to use as is. Equation 3, we're going to multiply both sides of it by negative 5, and in so doing we're going to add and then eliminate the x's. What that's going to look like is negative 5x plus 15y is equal to 10. When I add those two equations together, we end up with 13y is equal to 0. Well, if 13 times y is equal to 0, that means y itself is equal to 0. Now y equals 0 for all of the equations. So what I can do is rewrite equations 1 and 3, which I'll do down here. So for 2y plus z equals 3, if y equals 0, then that gives me right away that z is equal to 3. For x minus 3y equals negative 2, again, if y equals 0, that gives me directly that x is equal to negative 2. Now all that's left is for me to package this up nicely in an ordered triple, say x, y, z is equal to negative 2, 0, 3. So to recap, our general strategy when dealing with a 3 by 3 system is to eliminate a variable twice to end up with a 2 by 2 system, which we solve usually using elimination or substitution, and then we start that process of back substituting to get the other variables. Supposing we started with a 4 by 4 system, what we would do is we would eliminate the same variable 3 times, end up with a 3 by 3 system, and then guess what? Eliminate the same variable twice, end up with a 2 by 2 system, which we would solve by elimination or substitution, and then again work our way through a back substitution process to recover all of the variables. We're not going to do that in this video. Our last example, though, is a little bit interesting. We're given instructions, find real numbers a, b, and c so that the graph of the function y equals ax squared plus bx plus c contains the points negative 1, negative 2, 1, negative 4, and 2, 4. You see the word graph, you think you have to graph. We're not going to graph. What is meant when we say the graph of the function contains the points is that the point negative 1, negative 2, well, x is negative 1 and y is negative 2. For the point 1, negative 4, x is 1 and y is negative 4. And likewise for the point 2, 4, x is 2 and y is 4. What we're saying is these are 3 ordered pairs, 3 points that are on a graph. The graph, y equals ax squared plus bx plus c, is that of a parabola. This is just saying you've got 3 points, come up with the equation of a parabola. And the way we're going to do it is using a 3 by 3 system. Let's look at the first case, when x is negative 1 and y is negative 2. What that means is that x is negative 1 and y is negative 2. And so we end up with an equation that says negative 2 is equal to a times negative 1 squared plus b times negative 1 plus c. You see, we're just substituting negative 1 in place of x. We can do the same thing for the second ordered pair, where x is 1 and y is negative 4. X is 1 and y is negative 4 in that equation. And so, negative 4 is equal to a times 1 squared plus b times 1 plus c. Finally, we have the ordered pair 2, 4. Where x is 2 and y is 4. That means when x is 2, y is 4. And so we have the equation 4 is equal to a times 2 squared plus b times 2 plus c. the first equation becomes a minus b plus c is equal to -2. The second equation becomes a plus b plus c is equal to -4. And the third becomes 4a plus 2b plus c is equal to 4. So here we have a 3x3 system that was obtained by substituting 3 ordered pairs in turn into an equation. I'm looking at this kind of holistically here, and it looks like it would probably be, I don't know, a crapshoot between eliminating the b's and eliminating the c's. What I'm going to do is I'm going to go ahead and eliminate the c's. Labeling my equations 1, 2, and 3, what I'm first going to do is take equation 1 and subtract from it equation 2. So I have a minus b plus c equals -2, and to that I'm going to add -a minus b minus c equals 4. As it happens, both the a and the c get eliminated. We have -2b is equal to 2, which tells me straight away that b is equal to -1. I still need to pick a pair and eliminate c again. I need to know what's going on with a. I don't have enough information to back substitute yet. And so what I'm going to now do is take equation 2 and subtract from it equation 3. And so I have a plus b plus c equals -4. -4a minus 2b minus c equals -4. The c's will subtract out, and we end up with -3a minus b is equal to -8. Since b is -1, when I substitute that value, I end up with -3a plus 1 is equal to -8. So -3a is equal to -9, and a is then equal to 3. Now I have a and b, I need c. I'm going to use equation number 1, which is a minus b plus c is equal to -2, and substitute the value 3 for a, -1 for b, that'll make it 3 plus 1, and then we've got plus c is equal to -2. So 4 plus c is equal to -2, and so c is equal to -6. Now, remember what we were supposed to do was come up with an equation, right? The equation was y equals ax squared plus bx plus c, and we were supposed to fill in the constants a, b, and c, or the coefficients, which we can now do. We can say that y is equal to 3x squared, because a is 3, minus x, because b is -1, minus 6, because that's the value of c. We don't answer in an ordered triple this time because we were asked to find an equation. There it is.